Let's talk about some metrics that you can derive from a confusion matrix. This stuff is super important on the exam, guys, so pay attention. So let's revisit our friend the confusion matrix. Again, in this particular example of one, we have actual values going down the columns and predicted values across the rows. That can be different. But in this format, we have the number of true positives in the upper left corner, the number of true negatives in the lower right corner, the number of false negatives in the lower left corner, and the number of false positives in the upper right corner, okay? So make sure you understand where your true positives and negatives are, where your false positive and negatives are when you're starting to look at a confusion matrix. And again, that can vary based on the layout of the confusion matrix itself. Let's start with recall. So recall is computed as the true positives over the true positives plus the false negatives. You should seriously memorize this. You need to know this. It goes by other names as well, just to make things more confusing. So it's also known as sensitivity, true positive rate, and completeness. And completeness kind of harkens back to its original use in the world of information retrieval. You can also think of recall as the percent of negatives that were wrongly predicted. So it's a good choice of metric when you care a lot about false negatives. Okay, so fraud detection is a great example of where you might be focusing on recall, because a false negative in the world of fraud means that something was fraud, but you failed to identify it as fraud. You had a fraudulent transaction that was flagged as being perfectly okay. That is the worst possible outcome in a system that's supposed to be detecting fraud, right? You want to be erring on the side of false positives, not false negatives in that case. So recall, good choice of metric when you care about false negatives. Fraud detection being an example of that is true positives over true positives plus false negatives. Write that down, make yourself a little cheat sheet, cram on this stuff before the exam, okay? Let's make it real with an example here. So in this particular example of a confusion matrix, again, recall is true positives over true positives plus false negatives. We just pluck the values out of this confusion matrix. In this particular layout, true positives will be 5, false negatives will be 10. So we just say 5 over 5 plus 10, which is 5 over 15 or 1/3 or 33.33333%, right? So that's recall. Recall's partner in crime is precision, and precision is computed as true positives over true positives plus false positives. This goes by other names as well, including the correct positive rate or the percent of relevant results. So this is a measure of relevancy in the world of information retrieval. When should you care about precision? Well, it's an important metric when you care about false positives. Some examples would be medical screening or drug testing. You don't want to say somebody's, on cocaine or something when they're not. That would have like really bad effects on their life and career and stuff, right? So again, precision when you care about false positives more so than false negatives. Drug testing being a classic example of that. Again, it is computed as true positives over true positives plus false positives. And again, we'll dive into an example here. In this particular confusion matrix, the true positives will be 5. The false positives in this example are 20. So the precision is calculated as 5 over 25, which is 20%. There are other metrics as well. For example, specificity, which is the true negatives over true negatives plus false positive, also known as the true negative rate. Also, F1 score is a very common thing that's used. And again, you should memorize this formula too, guys. Write it down somewhere. That is 2 times the true positives over 2 times true positives plus false negatives. You can also compute it as 2 times the precision times the recall over the precision plus the recall. Either way works. Mathematically, it is the harmonic mean of precision and sensitivity. So if you care about precision and recall, remember recall and sensitivity are the same thing, F1 score is a metric that balances the two. If you know that your model doesn't just care about accuracy alone and you want to capture both precision and recall, F1 score can be a way of doing that. But, in the real world, you're probably going to care about precision or recall more so than the other. So it really pays to think about what you care about more. Using F1 score, in my opinion, is a bit of a shortcut, a little bit of laziness, but the exam may expect you to know what it is and how to compute it. Also, RMSE is often used as a metric. It's just a straight up measure of accuracy, and it's exactly what it sounds like, the root mean squared error. So you just add up all of the squared errors of each prediction from its actual true value and take the square root of it. That's it. So it only cares about right and wrong answers. It doesn't get into the nuances of precision and recall So if all you care about is accuracy, RMSE is a common metric used for that. Another way of evaluating your models is the ROC curve, that stands for Receiver Operating Characteristic Curve. And what it does is plot your true positive rate, or your recall, versus your false positive rate at various threshold settings in your model. So as you choose different thresholds of choosing between true and false, what does that curve look like? Basically, the way to interpret a ROC curve is that you want it to be above the diagonal line there. So the ideal curve would just be a single point at the upper left-hand corner, just a big right-hand angle where the whole thing is in that upper left-hand side of the graph, if you will, to the left of that diagonal line. So the more bent a ROC curve is toward that upper left corner, the better. That's how you interpret these things. We can also talk about the area under the curve, which is the area under the ROC curve, exactly what it sounds like. So you can actually interpret that value as the probability that a classifier will rank a randomly chosen positive instance higher than a randomly chosen negative one. So an AUC of 0.5 would be what you'd expect to see if you were at that diagonal line, right? So if you actually had the area underneath that diagonal line where things are no better than random, that turns out to be an area of 0.5, right? So that kind of makes sense. So if you see an AUC of 0.5 or below, that's useless or worse than useless. The perfect classifier would have an area under the curve, an AUC of 1.0. That would again be that perfect case where the curve is just this right angle with a 1 point at 0, 1 up there in the upper left-hand corner. That would include the entire area of that entire graph, which works out to 1. So AUC can be a useful metric for comparing different classifiers together, where the higher the value, the better. So there you have it, some common metrics for evaluating classifiers. Precision, recall, F1 score, ROC, and AUC are the important ones to remember. Again, make yourself a cheat sheet, guys. This stuff is important.